Good morning, students. Today we are going to discuss about electrophilic addition reaction of alkene, that is EAR. Very important. With the mechanism and the examples and exceptions and the rearrangements, everything we are going to be learn in this topic, electrophilic addition reactions of alkene. Let's see the reaction. Here it is a alkene. Alkene is reacted in the presence of reagent which is having electrophile and nucleophile. The electrophile is positively charged species or having the vacant orbital, and the nucleophile is negatively charged species or having the lone pair of electrons. Then one of the pi bond has to be shifted towards the carbon and forming the negative charge and the positive charge. Right? The negative charged carbon, the electrophile has to be attacked at the one of the carbon which is having the negative charge, and the nucleophile has to be attacked at the carbon which is having the positive charge. So like this, the new compound has to be formed. It is to be the alkane, right? Let us see the mechanism to understand very well. See here, the pi bond is shifted to the one of the carbon and it is getting that partial negative charge. When it is getting the partial negative charge, this electrophile will come and attack in this carbon, right? So now it is the slow step. Step 1, it is the slow step. Always slow step is the rate determination step. Now it is C double bond C. Here it is forming the positive charge, bond C, bond C. Here it is electrophile. Now to this carbocation, the whatever the remaining nucleophile is there, that nucleophile will come and attack at this carbocation. It is the first step. So now the nucleophile is to be attacking on this. This is the carbocation formation is to be the intermediate step. In this intermediate step, the carbocation is formed. Hence, the rearrangement can be takes place with respect to the carbocation. How the stability of carbocation is to be there with respect to that, it is to be rearrangement can be takes place. Now the first is the slow step, is the rate determination step. That's why this reaction is to be called as electrophilic addition reaction. The electrophile only deciding the rate of a reaction. Here the rate of a reaction is nothing but our average rate is equals to this alkene and also electrophile, because it's a slow step, right? So that reason the rate of reaction is to be depends on the alkene and the electrophile, not the nucleophile. Hence it is to be called as electrophilic addition reaction of alkene. Now the nucleophile is to be going to be attacked at the carbocation is based on the intermediate is to be formed as a carbocation. Hence the carbocation stability plays a major role on this addition reaction of electrophile. The nucleophile has to be attacked at the carbocation, which is having the more stable carbocation. The carbocation stability order. Benzyl carbocation is to be greater than allyl carbocation is greater than, tertiary is greater than, secondary greater than, primary is greater than methyl carbocation. So benzyl and allyl is to be the more stable due to resonance. More resonating structures, more stable. Due to resonance, allyl and benzyl are to be more stable. Then after tertiary, secondary and primary, due to hyperconjugation. Tertiary is to be more greater than secondary is to be more greater than primary. Then after CH3 plus. Let us see some of the examples how this nucleophile to be attacked at carbocation. Nucleophile attacked at the carbocation with respect to the Markovnikov's rule. What is the Markovnikov's rule means? The nucleophile should be attacked at the carbocation, the carbon which is having less number of hydrogen atoms or else more substituted carbon. That carbocation should be more substituted carbon or less number of hydrogen atoms in that carbon. That carbocation is to be substituted with the nucleophile, right? The addition with the nucleophile. Now it is nucleophilic addition reaction. That carbocation is to be the more stable, right? According to the Markovnikov's rule. The Markovnikov's rule product is resioselective product, right? Let us see some examples. Let's take one example. It is the alkene, the reaction with HCl. Now here the electrophile is H plus and the nucleophile is Cl minus. the H plus is to be attacked at the CH2 and forming the CH3 because it's a pi bond has to be shifted. Now here the carbocation is to be formed. Now it is which type of carbocation means secondary carbocation. Let's see another possibility. If the pi bond is to be shifted towards left, right? Now it is having the negative charge. Now electrophile is to be attacking at this carbon. That means hydrogen can be attacked at this carbon, that is CH2. Now it is forming that positive charge. Hence it is CH2Cl. Now this CH2 is positive, right? So now it is to be the primary carbocation. Now which is to be the more stable, right? Secondary is more stable than primary, right? Less number of hydrogen atoms. See here only one hydrogen atom is there, but here two hydrogen atoms are there. So it is to be the more stable when compared to the primary. So secondary is to be the more stable when compared to the primary. So it is a major product. So it is to be forming. It is not to be forming according to the Markovnikov's rule, right? The carbocation can be rearrangement takes place to get the stability. The rearrangement stability order is H minus. Remember, very very important. H minus is greater than benzyl is greater than alkyl group, tertiary greater than secondary greater than primary is greater than CH3 bond CH3. This is the stability order. That means rearrangement order. First H minus S can be rearrangement is possible means that only will be takes place. After that benzyl, then after alkyl groups, nothing but tertiary greater than secondary greater than primary, then after CH3, which is to be possible, that only will be takes place. Let's see some of the examples for the rearrangement reaction. Let's see some examples. The first one is a primary carbocation. Is there a possibility to form a secondary carbocation in this? Yes, this is secondary carbocation and also it is also primary. So now from this adjacent carbon, the hydrogen has to be shifted. This H2, this CH bond H, this hydrogen has to be shifted to this one. 1,2 hydrogen shift, 1,2 hydrogen shift, H minus can be shifted. Hence it is forming CH3 bond CH plus bond CH3. Now it is secondary. Secondary is more stable than primary. Hence the rearrangement can be takes place. Let's see the second example, right? Now it is secondary carbon. Let's see, it is the tertiary. Tertiary is there and it is also secondary. So secondary carbocation is there. Now the tertiary carbocation is more stable than secondary. Now this hydrogen can be shifted like this. Now what is the product has to be formed? CH3 bond C bond CH3 carbocation bond CH2 bond CH2 bond CH3, right? It is tertiary, more stable when compared to the secondary. Let's see the another example. It is to be there, it is a primary, it is to be tertiary, it is to be secondary, and it is to be tertiary. Now from this secondary to one of the hydrogen has to be shifted. Now what is the product has to be formed? CH3 bond CH3 bond CH carbocation, hydrogen shifted, right? So CH3. Now this is secondary carbocation. Adjacent is tertiary is possible. Now again this hydrogen shift can be takes place. And now the product is to be CH3 bond C bond CH3 carbocation bond CH2 and CH3. It is to be the tertiary. Is the more stable, right? Let's see another example. Now it is secondary. It is also secondary. But what is the difference between it is also secondary? What is the difference between this and this? So already having the carbocation and this is the difference is resonance stabilized, right? So when the resonance stabilization is there, then automatically it is to be the more stable when compared to the secondary and tertiary also. Hence this hydrogen has to be shifted to here. Then what is the product has to be formed? Let's see. Is the positive charge. This is to be the secondary and also resonance stabilized. Resonance stabilized. Hence it is to be the more stable. Like that, rearrangement can be happen. Not only this hydrogen shift and benzyl shift, uh, we can rearrange ring expansion and ring contraction as also takes place in these reactions. Let us see the examples. Let's see the one more example. It is the primary carbocation. Now the shifting is to be there. It is to be the tertiary carbocation. Now methyl shift is there, ethyl shift is there. Which is to be shifted? Now it is secondary, right? While shifting also, H minus is greater than phenyl is to be greater than tertiary greater than secondary greater than primary greater than then after methyl shift. Already we discussed it, right? So now secondary shift has to be takes place. That means this one has to be shifted to here. Now the product is CH3 bond C bond CH3 bond CH2 bond CH2 bond CH3. Here it is carbocation. It is also tertiary, right? Let's see the example 6. Now it is a primary carbocation. Second carbon is tertiary. So tertiary is more stable than primary. Then ethyl shift is there, isopropyl shift is there, which has to be done, right? This is tertiary and it is secondary. So tertiary is to be more favorable. Already we discussed the stability. So this isopropyl has to be shifted to here. So now the structure is CH3 bond CH2 CH3 bond CH2 bond CH CH3 CH3. This is the carbocation, right? Which is the more stable? Which is carbocation? Tertiary carbocation. Now it is also primary. Again it is tertiary. So tertiary means ethyl shift is there and also phenyl shift is there. Which is to be more favorable? Phenyl. Already we have a order. So now CH3 bond C positive bond CH2. Here CH2 CH3 bond phenyl group. So this is the, like this we have to rearrange the carbocation stability, right? Let's see the example 1. Now it is the product, the reactant is there. Now the pi bond is to be shifted here. It is to be forming that positive charge, which positive it is secondary, right? Now adjacent carbon is tertiary, right? The adjacent carbon is tertiary, then hydrogen shift is to be there. Hydrogen is possibility. Then hydrogen shift has to be takes place. Tertiary is more stable than secondary. So now it is forming tertiary carbocation. Tertiary carbocation. To this, the nucleophile has to be attacked. What is the nucleophile? I. So it is the major product. Not the iodine has to be attacked at this carbon. This is not a major product, right? Let us see the second example. Now it is to be the minus. It is to be the forming the secondary carbocation. Hydrogen will come and attack here, CH2 becomes CH3. Now this secondary carbocation. Adjacent carbon is tertiary. So methyl is there, ethyl is there. Which has to be shifted here? Ethyl has to be shifted here. Why? Because it is secondary. Secondary shift is more preferable than primary, methyl shift. So now the product is CH3 bond CH3 bond CH CH3 bond CH2 CH3, right? Now here carbocation. What is the nucleophile here? Br minus. The Br minus will be attacked at this carbon. Tertiary is to be the more stable. This is the tertiary is to be the more stable. This is also tertiary. The rearrangement can be takes place. Now it is also next third one is also. Let's see. This is having the iodine. It is a secondary carbon. So secondary carbocation is to be formed. So CH3 is forming. Hydrogen will be attacked here. H plus. Now I minus is to be there. I minus will come and attack here. But the adjacent carbon is, this carbon is, if the hydrogen is to be shifted, it is the benzyl carbocation, which is resonance stabilized, more stable. Benzyl is to be the more stable than allyl. Allyl is to be the more stable than tertiary, secondary and primary, right? So now benzyl carbocation is to be formed. Then from this hydrogen shift has to be takes place. Here that is the product has to be formed. CH plus bond CH2 bond CH3. Benzyl carbocation. To this carbocation, what has to be attacked here? I has to be attacked. Right. So this is the major product. The next one here, this is CH3. Here the secondary carbocation. Then what about this one? If the secondary carbocation is to be there, the next, the rearrangement can be takes place here. Let's see. If it is a secondary carbocation, right? Now this ring expansion has to be takes place. How, like, let us see. CH plus bond CH3. When the ring expansion, the steric hindrance, that means strain is to be decreases. When the energy has to be less, then the stability has to be more. Hence it is forming the 6-membered carbon chain and also CH3. Here it is positive charge. This positive charge has to be again nucleophile is what? Br minus. It has to be attacked here. Like this structure has to be formed. Because it is tertiary is more stable, right? Tertiary is more stable. Hope you are understanding. Then anti-Markovnikov's rule is there in the presence of peroxide, that is HBr, and CCl4Br2 is there with the mechanism. So more number of examples and mechanisms are there in these alkenes. So we will discuss further. Hope you understand. Please like, share and subscribe. Happy learning. Take care. Bye. Thank you.